Hi guys, this video is about heat transfer quick notes revision for GATE. Let's first discuss the syllabus of heat transfer. We have conduction, in which the topics are Fourier laws, Newton law of cooling, 1D steady state conduction for Cartesian plane, cylinder, composite wall, and conduction with heat generation for plane wall, cylinder, and fins. Then we have heat exchanger, in which we are going to discuss double pipe heat exchanger, LMTD for parallel flow and counter flow, shell and tube heat exchanger, and effectiveness of NTU. And then we have convection, in which we have forced and free convection. Forced convection have Prandtl number, Nusselt number, and Reynolds number. Circular pipe flow, heated flat plate flow analogies. And in free convection we have Grashoff's number. And then we are going to discuss boiling and condensation. In radiation, we have Stephen-Boltzmann law, view factor, radiation network, and shielding. So our first topic of heat transfer is conduction. Conduction is basically in presence of temperature gradient, energy transfer occur in direction of decreasing temperature, and there is stationary medium present. So the very first law in conduction is Fourier's law, which states that heat flux, Q double dash is heat flux, is equal to minus dt by dx. Dt by dx is driving force, which is nothing but heat transfer rate upon area. And rate of heat transfer is noted as minus Ka dt by dx. Unit is Weber per second, Joule per second. Flux unit is Weber per meter square. Heat transfer rate unit is Joule per second. And where K is our thermal conductivity, its unit is Weber per meter Kelvin. And thermal conductivity of solid is more than liquid, and for liquid is more than gas. Thermal diffusivity, which is alpha, is nothing but K by rho Cp. K is conductivity, rho is density, and Cp is specific heat, which is equal to heat transfer ability by energy storing ability. Next is general energy balance. Energy in minus energy out plus minus heat generation is equal to accumulation. Energy going in is Qx, then minus coming out is Qx plus dx plus heat generation Q dot V. Q dot is our heat generation, is equal to rho Cp dt by dt V, in which capital T is temperature, small t is time. In 1D, it is denoted as del square T by del x square plus Q dot by K is equal to rho Cp del T by del T, where Q naught is our energy generation rate per unit volume. And it can also be written as, using that converting thermal conductivity into thermal diffusivity by this formula, it can also be written as del square T by del x square is equal to 1 by alpha del T by del T when and there is no heat generation. In that case, this equation can be used. And this equation can be written in 3D form, in del square T by del x square plus del square T by del y square plus del square T by del z square plus Q naught by K is equal to rho Cp del T by del T. Next we have is Newton's law of cooling, in which conduction takes place inside and convection is taking place outside. This is basically balance between flux inside solid and flux outside solid. So we have a solid and the temperature on its surface is noted as Ts and outside temperature is T0. So conduction is taking inside the solid and convection is taking at the outside surface. So the flux would be equal to H, which is heat transfer coefficient, into temperature outside minus temperature on the surface. And we know that flux is nothing but minus K dt by dx at x is equal to 0. At this point, at x is equal to 0, H into T0 minus Ts. Next we have resistance offered by system towards conduction, which is noted as RC, which is nothing but delta T, change in temperature, by Q, rate. It can also be written as by putting the value of K Q, which is Ka into T delta T by L, we get RC is equal to L by Ka. And to calculate overall resistance, it is delta T, temperature overall, by rate. Then this is a small case, heat conduction for infinitely long surface. Like if we have an infinitely long surface, then, and this is like Ti is at the temperature at the tip of the starting point of the surface, and T infinity is outside temperature, and we have to calculate T at any distance x, and the total length of the surface is L, and at any distance x from the surface temperature, Ti temperature, we have to calculate temperature at this point. So in that case, we are going to use this formula, which is nothing but T at x at this point minus T infinity, which is outside temperature, upon Ti temperature on the one end minus T infinity outside temperature, which is equal to e to the power mx. Mx can be calculated as under root hp, where p is our perimeter, by Ka, area. M is equal to under root heat transfer coefficient into perimeter upon thermal conductivity into area. Next we have 1D steady state conduction, and no heat source is there, that is Q0 is equal to 0, and it is steady state, so no energy or heat generation is there, which rate that Q is constant, rate is constant, which means that heat generation would be 0. So the first case in this is for general equation, or for a slab. We have a slab of L length, and temperature on this surface is T1 and on this surface is T2. So we have the equation comes out to be K d square T upon dx square is equal to 0. And to calculate T, temperature at any given point on this slab, is equal to T2 minus T1, temperature of side 2 minus side 1, into x by L. X is at any given point, at any x given point we have to calculate the temperature, x by L, total length of the slab, plus T1. And Qx, which is our rate, is equal to minus Ka dt by dx, which is equal to minus Ka T2 minus T1, change in temperature, by L, length of the slab. And our resistance of conduction would be L by Ka. In case of cylinder, we have a coaxial cylinder. So the coaxial cylinder is one in which like two cylinders are there with common center. So the radius of first cylinder is R1, and temperature on this surface is T1, and outer radius is R2, and temperature here is T2. And so the formula for this is d square T by dr square plus 1 by r dt by dr is equal to 0. So this is general formula for any cylinder. It can be used for any cylinder, and for coaxial cylinder, which usually comes, so in which if we have to calculate temperature at any given point on the surface of the cylinder, we can use this formula. T is equal to T1 minus T2 upon ln R1 by R2 into ln R by R2. R is at any, to calculate temperature at any given radius, plus T2. To calculate rate, QR is equal to minus 2 pi KL T1 minus T2 upon ln R1 by R2. And it is given that stating the condition when T1 is greater than T2, which means that the temperature at inside is more than temperature outside. So resistance would be ln R1 by R2 upon 2 pi KL. Then we have composite wall. Composite wall is in which 2-3 surfaces are joined, and solid surfaces are joined, and fluid is flowing from the outside. And in this, like as we can see in this example, we have three slabs put together, and fluid 1 and fluid 2 is flowing from the outside, slab A, B, C, and temperature for slab A is T1 and conductivity is K1. For slab B we have T2 temperature, K2 conductivity. Slab C we have T3 temperature and K3 conductivity, and all of these lengths are given of slab L1, L2, L3. And outside fluid temperature is T infinity 1 and its heat transfer coefficient is H1. And for this then fluid 2 we have H2 heat transfer coefficient, and temperature is T infinity 2. So as you can see from the diagram, for the two medium, like for the fluid and this surface, convection is taking place. As we know that convection is heat transfer between two medium. And for this slab, like if we see, when heat goes from this part, there is convection is taking place, and for heat transfer between this slab only, conduction is taking place. So like if we see for one slab, this is fluid flowing, and between the slab and the fluid convection take place, and in between the slab conduction take place. So we are going to calculate our total resistance. For that we can see that convection is taking place between fluid 1 and slab A, then convection is between fluid 1 and slab A, then conduction in between slab A, then again conduction in slab B, then conduction in slab C, after which we would have convection between slab C and fluid 2. So conductive, we have already studied about conductive resistance, which is L by Ka, and convective resistance is noted as 1 by Ha. H is convective heat transfer coefficient into area of the slab. So to calculate this resistance, overall resistance of a composite wall, we are going to draw a network of resistance. So from temperature T infinity 1 to temperature 1, what we are having is convection which is noted as R1. So convective heat transfer would be 1 by H1A. Then for slab A, in between the slab A, so there we have R2 resistance, conductive resistance L1 by K1. Then for slab B, we are having again conductive resistance, which is L2 by K2A. Then for same goes for slab 3, again conductive resistance L3 by K3A. Then after which between the slab 3 and fluid 2, we are having convective resistance, which is 1 by H2A. So we have already studied that resistance, total of resistance would be summation of all the resistances. So R overall is change in T overall by Q, which is nothing but 1 by UA. What is U? U is our overall heat transfer coefficient. 1 by U is given as 1 by H plus L by K, that is conduction plus convection, to calculate overall heat transfer coefficient, and Q comes out to be UA delta T. So if we are given any question to solve composite wall situation, then we can use this resistance network to calculate our total resistance and overall heat transfer coefficient. Okay, if area, which is used to calculate our overall, and so if area is given as 1, or if in case area is not given, in that case T1 minus T infinity by R1 is going to be equal to T2 minus T1 upon R2, and so on. So this means that T1 minus T infinity 1, the temperature difference between these points, upon resistance 1, resistance of this part, is equal to temperature difference between these parts and resistance between them. So, and R is equal to L by K. Next we have is R thermal resistance, which is delta T by Q. And if Q is equal to T, if Q by T is equal to delta T by R thermal resistance, then T1 by T2 would be equal to R1 by R2. We know that Q is equal to delta T by R, and if Q with respect to time is equal to delta T by R thermal, then in that case T1 by T2 would be equal to R1 by R2, and T is our time. Now we have conduction with heat generation. So general formula for this would be K d square T by dx square plus Q naught, which is heat generation, is equal to 0. So for plane wall, we have the equation T at x, any given point x, is equal to Q naught L square by 2K. L is the length of the wall, into 1 minus x square by L square. Like this is our wall of L length, and we have to calculate T at any given point x. This is x distance plus Ts. So Ts is our temperature on the surface. Ts on temperature on the surface of the wall, and T naught is temperature at the center of the wall. Like if this is a wall, then T naught would be temperature at the center of wall, and for length L, Ts is on temperature on the surface. So T at any temperature at any distance x minus temperature on surface upon temperature at center minus temperature at surface would be equal to 1 minus x square by L square. Like for a wall, temperature at center T naught and temperature on surface is Tx. To calculate temperature at any point x, we have to use this formula. And if there is adiabatic boundary given, like an adiabatic boundary is given, then in that case temperature at any point x would be Q naught L square by 2K plus temperature on surface. And Q naught, our Q naught is calculated as temperature at center minus temperature at surface by 2K by L square. One point to be noted is that resistance concept is not used if net heat transfer rate is not constant. We have to remember this point for solving questions. Then we have cylinder with heat. So we have a cylinder and its radius is given as R0, and the temperature at surface is Tx, and then we have to calculate temperature at any given radius R. So any given distance from the center is R is equal to 0, so that would be Q naught R square by 4K into 1 minus R square by R naught square. R square is the point on which we have to calculate the heat, upon R naught is the radius of the cylinder plus temperature at surface. So to calculate temperature at center, T naught would be Q dot R naught square upon 4K plus temperature at surface. So temperature at radius R minus temperature on surface upon temperature of center minus temperature at surface is equal to 1 minus R square upon R naught square, and Q dot would be temperature at center minus temperature at surface into 4K by R naught square. Then we have a case of hollow sphere. That this is a hollow sphere with the inner radius is R1, then the next radius is R2, and final radius is R3. Like there are 3 surfaces, so two material hollow sphere. This is an example special case. So in that case, Q would be equal to, rate would be equal to delta T by total resistance, and we know that total resistance is resistance of R1 plus R2. So R1 would be our radius 2 minus radius 1 upon 4 pi k R1 R2, and resistance 2 would be radius 3 minus radius 2 upon 4k R2 R3. Then next we have extended surface. So extended surface, like this is an example drawing of extended surface or fins. So this is our base, and on which extra area is added. These are extra fins or area is added, and this increases the heat transfer. So this added area also causes heat loss and conduction take place here. So to calculate efficiency of fins, and eta f is equal to qf by q max, which is equal to qf by h. Q max we calculate from Newton's law of cooling, which I've studied earlier. So qf by h as area of the surface minus Tb minus T infinity. Tb is our temperature of base, like from which this is the base from which the fins are attached. So Tb is temperature of base minus T infinity outside temperature, which is nothing but actual Q by maximum Q. Like actual Q is what heat a normal base surface can generate, upon Q maximum is what the new heat rate is generated after the addition of fins. So Q max, which is maximum heat transfer, is equal to HAS, temperature at base minus temperature at infinity. For adiabatic condition, efficiency would be eta would be tan H ml by ml. So when length is 0, like if the length of fin, this is the length L of length of fin is 0, then efficiency would be 1. And when the length of fin tends to infinity, like if the fin is extremely long, then efficiency would be 0. So to calculate overall efficiency, we have this formula, which is Q total by Q max, which is equal to 1 plus NAF by AB into eta f minus 1. Capital N is our total number of fins which is added, and AF is total surface area of all of the fin upon AB, which is surface area of the base, like you have discussed earlier. These are the n number of fins, and this is the base surface. So total surface AF would be total surface of all these fins, and AB would be the surface area of this base. So in case of an infinitely long fin, like if our fin which is added is infinitely long, in that case theta by theta E would be equal to E to the power minus mx. And if two rods having one end inserted in a furnace, this is a case, like two rods are having one end inserted in a furnace, then x1 by root k1 would be equal to x2 by root k2. When parameters are same for fins, then m1x1 is equal to m2x2. Then in that case, under root h into parameter upon k1ax1 would be equal to h into parameter upon k2ax2. These would be equal if the parameters of the fins are same, and m is r under root h into perimeter upon conductivity into area. Next we have insulation. Insulation, when a surface is insulated, then addition of so we have supposedly a cylinder of radius ri, and insulation is added. Now the increased radius is r0. So the inside temperature was Ti, and the temperature outside of the insulation, this is in our insulation, this portion, this, so outside temperature is T0 and heat transfer coefficient is H. So our critical radius, like how much this radius, how much radius should be added for insulation. That would be K by H, conductivity by heat transfer coefficient. So critical radius is how much radius of insulation should be added to get the maximum heat transfer, because after, when we add insulation after critical radius, then there is decrease in heat transfer. This is the curve that depicts that by increasing the radius of insulation till the point RC, this is RC point, we get Q maximum. Then if we increase the radius further, there is decrease in our heat transfer. So Q would be 2 pi L into T inside minus T infinity, T outside, upon ln R naught outside radius by inside radius upon K plus 1 by R naught H outside radius into heat transfer coefficient.